All right, let's ride this wave. We're going deep today into wave motion. You've sent in some really interesting stuff, and I'm excited to dive in.
Waves are fascinating. It's energy, really, moving around, rippling in a pond, or blasting out of speakers. It can even travel through space.
Whoa, okay, so maybe back up a sec. Like, at the most basic level, what even ISE a wave?
You imagine a pebble, right? And you toss it into a still pond. You see ripples, right, going outward.
Yeah, of course.
That's wave, a disturbance moving through something, carrying energy along with it.
So it's not the water itself moving out, it's the energy, like the pattern.
Right. The water molecules are just bobbing up and down. They pass the energy to their neighbors, making that ripple.
Cool, I can see that. So like sound waves, the air isn't going from the speaker to my ear, it's the energy.
Exactly. The speaker vibrates, making these little pressure changes in the air. They spread out, and when they hit your eardrum, it vibrates too. Your brain then says, hey, that's sound.
Wild. So much going on that we don't even think about. So we got these waves moving through stuff. How do scientists even, categorize all the different kinds?
Good question. That's where classifying comes in. First, does it need something to travel through, like our water and sound waves?
Okay, makes sense.
Those are mechanical waves. But light, that's electromagnetic. It goes through space, no problem.
No way. So the fun's light, it doesn't need anything to travel to get here. Mind blown.
Yep. So, those cool space movies? Explosions everywhere.
Yeah.
Total silence. No air for sound to travel through in space.
Well, that kind of ruins the fun. Okay, so mechanical, electromagnetic, what other ways are there?
How the energy movies is another one. Progressive waves, the energy keeps going outwards, like our pond ripples.
Right.
But stationary waves, the energy is kind of stuck in one spot, like a guitar string vibrating.
Stationary. But how's a wave not moving?
It's not that the bits inside aren't moving. The whole pattern doesn't travel outward. It's like the energy bounces back and forth in a confined space, but making a steady pattern.
Okay, so the wave itself isn't stationary. It's the energy pattern that's stuck.
Exactly. We'll talk more about those later. They're super important for, instruments and stuff that vibrates.
I'm intrigued. But back to those tiny bits,
Yeah.
Moving around. How do they actually move in a wave?
That's transverse versus longitudinal. Transverse, the bits move perpendicular to the wave's travel. Think of a wave on a string. Wave goes sideways, but the string moves up and down.
Like that wave people do in stadiums. Each section goes up and down, but the whole wave goes around.
Perfect. Now, to get a transverse wave, you need something called shearing. It's like the ability to change shape without changing volume, bending a metal rod. That's shearing.
Gotcha. But water doesn't really shear, right? It just flows.
Exactly. That's why you mostly see transverse waves in solids or on top of liquids, but they're common. Light waves are transverse, and so are those earthquake waves, the seismic ones.
Whoa, so earthquakes make the ground go up and down. That's scary.
It is, but it shows how much energy these waves carry. Now let's switch to longitudinal.
Okay, hit me with a different motion.
Longitudinal, the bits move parallel to the wave's travel. Think of a slinky. Push one end, you get a compressed part. As that travels, it's followed by a stretched out part.
So sound, it's like pulses of high and low pressure moving, and our ears pick that up.
Precisely, and that's just one example of what longitudinal waves can do.
Crazy cool. So all these waves carrying energy, they all share some traits though, right?
You bet. And these traits are key to understanding how waves act. Wavelength, frequency, time period, and amplitude.
Okay, break it down. Wavelength, I'm guessing that's the length of one whole wave.
Yep. Distance between two crests or two troughs, the top and bottom parts.
Frequency, that's how many waves go past a spot each second.
Exactly. Measured in hertz, high frequency sound, lots of waves packed close. We hear that as high pitch.
So piccolo's higher frequency than a tuba. Makes sense. Time period, that's just the opposite then, right? Time for one wave to pass.
Nail it. And lastly, amplitude. Basically, how strong the wave is. For our string, it's the height of the crest, or how deep the trough is.
A bigger wave, more amplitude, more energy, like tsunami versus a little ripple.
Perfect. They're all related too. More lays per second, shorter wavelength. Gotta squeeze them in.
This is making sense. So we've got waves, their traits, energy moving around.
But the wave equation always seemed tough. Can we get it without the math?
Sure, it looks scary, but it's really saying how a wave's movement, time, and position are linked. Picture one spot on our string wave. The equation says that spot's acceleration is tied to how far it is from its rest spot.
So the further out, the faster it wants to snap back, like a rubber band.
Yep, and that acceleration depends on the string's tension and how heavy it is. elegant equation really gets to the heart of wave motion.
Well, I'll take your word for the elegant part. What about intensity? We hear that a lot, like for sound and light. How's that fit in?
Intensity is power. How much energy is flowing through an area? Think concert speaker versus a whisper. All about the intensity. Higher intensity, more energy per area.
Makes sense. Is that where the inverse square law comes in? Vaguely remember that from physics.
It is. Basically, for a point source like a light bulb, the intensity drops off real fast with distance. Double the distance, intensity's down to a quarter.
That's why a lamp's dimmer further away. Not just the light spreading, it's actually getting weaker fast.
Right. And it's true for all sorts of waves, from sound to light, even those gravitational waves out in space.
Now that's cosmic. Okay, ready for some more mind-bending stuff? What about superposition? Heard that makes waves do wild things when they meet.
This is where it gets fun. Superposition means when waves are in the same place, their effects just add up. They pass through each other, no problem.
So two waves in the same spot, they just combine. Wild. What happens then?
All sorts of outcomes. Interference, where they either boost each other, making a bigger wave, constructive interference.
So two crests line up, boom, bigger wave.
Right. Or they cancel out. Destructive interference, like noise-canceling headphones, using that to block sound. And if a crest and a trough meet, they, poof, disappear. It's like wave wars out there.
It is. Then there's beats, when two waves are slightly different frequencies. They make that wah-wah sound, like instruments a bit out of tune.
This is incredible. It's like there's this hidden world of waves all around us, always interacting.
And we've only just begun. So much more to discover about how waves act and what they do.
Well, I'm on board for this wave ride. Let's keep going and see what other amazing things we can learn.
Back again for more wave action.
You bet. Ready to ride this wave of knowledge further. Before the break, we were getting into superposition, waves bumping into each other. It's wild that adding waves can make such crazy stuff happen.
It really is. And speaking of crazy, those stationary waves we mentioned, super important. They show superposition in action, and they're behind, like, music, and why bridges don't fall down.
Okay, stationary waves. I'm still trying to picture a wave that doesn't move Z. You said it's about them reflecting back, right?
Right. Imagine a rope tied at one end, held tight at the other. You flick it, wave goes down. When it hits the tied end, it reflects back.
Okay, so wave going, then its reflection coming back. Then what?
Superposition time. As they overlap, they interfere. Some spots, they'll always add up, making a big peak. We call that an antinode. Other spots, they'll always cancel out flat. That's a node.
Like a wave tug of war. Some spots get the full force, others, nothing.
Exactly. And that makes a stable pattern, the standing wave. Rope's still vibrating, but the wave shape stays put.
So not that the rope's still, but the energy is trapped in that pattern.
You got it. And here's the cool part. The node and antinode spots depend on the wave's frequency and the rope's length.
So different frequencies make different patterns. Like each one has its own fingerprint on the rope.
Yep. And the frequencies that make stable standing waves, we call those harmonics. The lowest one is the fundamental frequency, that's like the basic note, but it can vibrate at higher ones too, making the sound richer.
So one rope, many tones, depending on the wave, like hidden potential in plain old string.
It is, and that's how instruments work. Guitar string, you pluck it, wave goes back and forth, standing wave. Pressing the string changes its length, so different frequencies fet.
Shorter string, higher pitch, that's why pressing makes the note go up.
Exactly. Tension matters too. Tighter string, higher bass frequency, higher pitch. That's what tuning pegs are for.
Mind-blowing. All the music we hear, it's really standing waves, like physics hidden in the music.
It is. And not just strings. Wind instruments, flutes, clarinets, they use standing waves too, but with air inside.
So instead of a string fixed at both ends, it's air trapped in the tube.
Right. Blow into a flute, you make a disturbance, a wave goes down the tube, it reflects back, interference happens, standing wave.
Tube's length controls what frequencies fit. Hence, different instruments, different notes.
You got it. The instrument's shape matters too, how the waves bounce around. And those keys and valves, they change the air column's length so you get different notes.
So much science in making music. Art and physics all mixed up.
Totally. And this whole resonance thing, things vibrating at their natural frequencies, that's everywhere, not just music. Bridges swaying, radios picking up signals, all that.
So it's not just pretty sounds. Resonance is practical too.
Oh, yeah, big time. Engineers got to think about bridge resonance so they don't, shake apart in the wind. If the wind's gusts match the bridge's natural vibe, things can go bad fast.
Okay, that's a little scary to think about. So knowing about resonance keeps things safe.
It does. On a less scary note, radios use it too. Tuning to a station, you're making the radio vibrate at the same frequency as the station's signal. So it picks that one up, ignores the rest.
Like a selective amplifier, picking out the exact frequency we want.
That's a great way to put it. Shows how this one idea, resonance, all because of waves and how they reflect, it impacts so much, from music to tech we use daily.
This deep dive is blowing my mind. Never realized how much physics was going on all around, like birds singing, radios.
We're just getting started. There's a whole universe of waves out there still to explore.
Well, I'm riding this wave all the way. What else can we discover about these amazing waves? We're back, still diving deep into waves. From ripples to standing waves, this has been a wild ride.
It has. And, we've seen how important waves are for, everything. From how music works to, well, the universe itself.
It's true. I used to think waves were just like at the beach. Now I see them everywhere. It's crazy. All this hidden energy constantly moving and shaping our world.
That's what's so cool about this stuff, right? You start seeing how everything's connected, all these different things, and it comes down to these basic wave ideas.
Totally. We talked about sound waves, water waves, even light waves. But there's one we haven't gotten to that always seemed kind of mysterious: gravitational waves.
Those are something else. Those are like ripples in space-time itself. When super heavy stuff, black holes, neutron stars, that kind of thing, when they speed up, they make these waves.
Hold on. So not through air or water. They're actually like warping space and time. My brain's melting a little.
It is mind-blowing. Imagine space-time like a sheet stretched out. Something heavy moves fast, it makes a dent, a ripple in that sheet. That's a gravitational wave, stretching and squeezing space as it goes.
So like the universe is ringing when black holes smash together. But if they warp space itself, how do we even measure them?
Yeah.
Wouldn't our instruments get warped too?
Good point. It's tough, super tough. You need these crazy sensitive detectors. They can measure teeny tiny changes in distance, like smaller than an atom.
Whoa.
Lasers and mirrors, they measure the distance between things super precisely. A wave goes by, that distance changes just a tiny bit.
So we're talking like top-level science here. But just detecting them is amazing. What can they tell us that we couldn't learn any other way?
They're a whole new way to look at the universe, literally. We can study stuff that's invisible to normal telescopes. Black holes merging, neutron stars crashing, things like that. Tons of energy all going into these waves.
It's like we gained a new sense, like hearing the universe.
Exactly. And different sounds tell us about what made them, right? These waves, they tell us about those massive objects and what happened.
A whole new type of astronomy using these cosmic ripples.
It is, and we're just starting out. As we get better at finding them, who knows what we'll learn?
This wave journey has been incredible, from little ripples to the very fabric of space and time, and seeing how it all ties into, everything around us.
And like we've said, there's always more to find out. New discoveries all the time, and each one shows us more about the universe.
Well, I'm excited to see what's next in the wave world. I have a feeling the best is yet to come.
Me too. So keep listening, stay curious, and maybe you'll discover some amazing wave stuff yourself.